Next, we will take a look at some more examples using natural logs. In this question, we're asked to write the following expressions as a sum or difference of logarithms. So here we have natural log of quantity x squared times y cubed over z. And because we have natural log of a quotient, we can write it as difference of two logarithms based on one of the properties from the previous page. So that's exactly what I did here. That's ln of the top minus ln of the bottom. But now that you have another product within the first ln, you can further break that apart as the sum of two logs. So that would be ln x squared plus ln y cubed. And the last term still there, minus ln z. And in the last part of the answer, I will simplify this even further by using property number 4, and that is you can bring down the power of 2 up front as a coefficient. So here we have, instead of ln x squared, I wrote 2 ln x, plus instead of ln y cubed, I wrote 3 ln y, and the last term has been copied as it is. Now, can you simplify the next one? Natural log of the square root of a times b. So my suggestion is first, think of square root as 1/2 power, and you can first bring it up front as a coefficient using property number 4. And then in the second step, a times b within a log, it can be broken down as log of first plus log of the second. In this case, it's log base e or ln. So here we have 1 over 2 times quantity ln a plus ln b. In the next example, we'll do quite the opposite. We are given an expression that consists of sum or difference of logs, and our job is to write this as a single logarithm. So in this situation, first thing to do is to get rid of each of the coefficients and write them up as powers, and then we can utilize those addition or subtraction rules. So first of all, getting rid of the coefficients and writing them as powers, we get the following. Notice that the 1/2 power is what gave me z to the 1/2, which is the square root. Next, if you have ln of x cubed minus ln y to the 4, that can be written as a single ln of the quotient of x cubed over y to the 4th. But because there's another minus here, technically, you could have first factored out the negative from these two. So these two will be a product, natural log of the product of the arguments. But then between this and everything else, there's a subtraction. So the final answer turns out to be as follows. Natural log of x cubed divided by y to the 4 times square root of z. And why did y to the 4 and square root of z, they both appeared in the denominator? Because they both had a minus sign in front. Next, we're going to do some examples with solving equations, whether they are exponential equations or logarithmic equations. We're going to need logs in the solution process. So for example, e to the x equals to 25. What is x? That's the question. We could do a trial and error, of course. Like we could do e to the second, e to the third, and e to the fourth, and try to approximate, see which one is closest, and further narrow it down. But that's a lot of work, a lot of trial and error. Instead, we had learned previously that if you have something in exponential form, you can write it in logarithmic form as x equals logarithm base e of 25. This is from our property number 1. So this power can be represented as logarithm base e of 25. And again, if you want to think backwards, how would you go from this to the exponential form? You would need to take e raised to the power of x equals to 25, and that's exactly what we had in the given problem. But there is even an easier way to do these questions, and let me show you how. Given the equation, if you realize that the unknown appears as the exponent, one thing you can do is you can apply natural log to both sides. So that's what I did, apply ln to both sides. Then For the left-hand side, you can use property number 4 to bring x down as a coefficient, which is what I did. And again, ln e is 1. You could have also just simplified right away. Ln e to the x is right away just x. That would be another way to do it. And therefore, we got the same answer. And mainly, x is equal to ln 25. Again, log base over here, of course, is the same thing as ln. Let's take a look at the next example. Three to the x equals to 100, solve for x. So once again, the moment you realize the unknown appears in the exponent, it's a good idea to apply natural log to both sides. Now you can technically apply logarithm to any base. You can also apply log base 10, but here we're having more practice with base e, so I'm applying ln to both sides. Then, once again, using one of the properties, bring the x down on the left-hand side. So now you have x ln 3 equals ln 100. And then to isolate x, divide both sides by ln 3. And we have our answer as ln 100 over ln 3. Use a calculator to evaluate both the numerator and the denominator. And the answer is 4.19. What about something like the next example? 5 times 2 to the x equals 25. The question is once again to solve for x. Now the unknown is x, which is the exponent, so you might be tempted to apply natural log or log to any base to both sides. However, notice that in front of our exponential expression there's a coefficient, the 5. So you couldn't really apply natural log right away and bring the x down. The property wouldn't apply when you have something times a quantity to the power x. So let's first get rid of the 5 by dividing both sides by 5. So divide both sides of the equation by 5, and we're going to have 2 to the x equals 25 over 5. In other words, 2 to the x equals 5. And now you could go ahead and apply natural log to both sides, which I did, and again bring the x down. So now we have x times natural log of 2 equals natural log of 5. And do you see the last step, which will be simply dividing both sides by ln 2. And there we have our answer. In those examples, we did solve exponential equations, but at times you might also be presented logarithmic equations, such as, say, log of x is equal to 2, solve for x. In that situation, again, this particular one is something we've already done previously because this is base 10. The answer will be, as we had seen previously, x equals to 10 to the power of 2, because again, the hidden base is 10, and the number you would have to write here is 10 to the second power so that you could get an answer of 2. Or using the little diagram we had, basically 10 to this power will equal to that. And so you can write x equals 10 to the power of 2, or simply 100. And in this situation, ln of x equals to 3. Again, the question is to solve for x. And in this situation, the unknown or the hidden base is e. So we can say that x is equal to simply e to the third. And you can evaluate that using your calculators. So it turns out to be that x is equal to roughly 20.09. And again, e is in your calculator, it's really 2.718, but in your calculator, usually you need to use second function, ln key, to access your e to the power key, and then all you have to enter after that is 3, and the end result of all of this on the calculator screen will be e to the power of 3. And let's take a look at one more example using solving logarithmic equations. Here we have natural log of 2x minus 7 equals to 2. Let's solve for x. So once again, the hidden base, anytime we use natural log, the hidden base is e. So let's get rid of the logarithmic form by saying e to the second power equals to 2x minus 7. So that's what I did. And you can simplify e squared using your calculator. roughly 7.39. And then this becomes a simple linear equation. So add 7 to both sides and then divide by 2. And that will give us the answer. And I must add that typically when you solve a logarithmic equation, you should technically check your answer. And if you ever end up with natural log of a negative quantity, then you will have to reject the answer uh, because natural log of a negative value is undefined. Okay, uh, in the next segment, we will take a look at an application of logarithms involving half-life.